Hi, today we're talking about section 15.3, which is a section on triple integrals. And our learning goals, as you might assume, are to think about visualizing triple integration. We're going to do triple integration over boxes, and we're going to see the three-dimensional version of Fubini's theorem. In addition, we're going to find volumes of solids in R3 using our triple integration technique. And we're going to practice interchanging the order of integration within triple integration problems. So to start our discussion today about triple integration, we're going to look at a motivating example that uses density. So if you recall from your physics classes, or maybe you don't recall, that's okay, that density is a measure of how much stuff is in something, essentially, and the density of an object times the volume of the object yields the mass of the object. And the reason why this is important is because this is a measure of a three-dimensional object, and we're going to be talking about three-dimensional objects today. So let's say that we have some object, and this object doesn't have uniform density. Most things that we talk about have uniform density, meaning that the density is the same throughout the object. But for some objects, let's say if you were doing a really fine sample of some type of fluid flow, this fluid might have different densities at different places in the fluid. So at the top of the fluid, it might be less dense than at the bottom of the fluid. Let's say that my density function is given by rho of x, y, and z. Meaning that if I find some point in three-dimensional space that has coordinates x, y, and z, I can plug that point into my density function, and it would tell me exactly how dense it is right at that point. So as I plug in a point, let's call this point up here as the point A, B, C. Right at this point, the point A, B, C, we can calculate and find the density at that point by plugging the point ABC into my density function. Now all of this is just a conceptual setup to get us to the idea of 3D integration. So the real question is, I want to know the mass of some object if the density is not constant. So as I move throughout this object, I'll draw a picture of my object. Let's see. Let's say we have some object in three-dimensional space, and it has, it's sort of rectangular-ish. Here's my pseudo-rectangular box that has some sort of curvy top. Right? So here's my three-dimensional object, and I want to know what is the mass of this object. My density is variable, meaning that at each point here in space I'm going to have a different density output. And the volume is something that I'm going to need to calculate because I know that the density times the volume is going to give me the mass of the object. The whole idea behind three-dimensional Riemann integration is exactly what we saw before. Is that instead of breaking up this volume into slices, which is what we did in one-dimensional functions, or breaking it up into little rectangles, now we're going to break it up into little cubes. So I'm going to take some cube in here. Here's my cube. I'm drawing it in blue. And the dimensions of this cube are going to be delta x is the depth of the cube, delta y is going to be the width of the cube, and delta z is going to be the height of the cube. And we can see that if I measure what the density for this tiny cube is, and I add up all of the cubes that take up all of the space within this object, so I could keep counting all of these cubes, breaking up my entire volume into a bunch of cubes. Obviously, it's an approximation with cubes. If we take the limit of all of those cubes, though, making those cubes tinier and tinier and tinier and tinier, that's exactly what we get with triple integration. Formally, what I mean is, I'm going to sum up a whole bunch of cubes. My cubes are going to be, here, maybe I should write out what I mean. X sub I, y sub j, z sub k. So this is my density function, and I'm evaluating the density for one cube. One cube is going to have the density x sub I, this is my I, my y sub j, and my z sub k point, somewhere in that little cube. And so the mass of this one cube is going to be the density of the cube times the volume of the cube, which in this case is delta x, delta y, delta z. But this is just for one cube. Now I need to sum over all the cubes in the x direction, all the cubes in the y direction, and all the cubes in the z direction. This is just a bunch of formal notation. This formal notation I don't care about. This is the motivating idea behind what a triple integral is, which when I take the limit of this, as the number of q's goes to infinity, L, N, M approach infinity, that's exactly where I get my integral. This becomes the triple integral of my density function, x, y, z, dx, dy, dz. And this integral is taking place over my volume W. In this case, we set it up so that our volume had variable bounds, and I'm just going to call the volume W. That's what three-dimensional integration looks like. Let's go ahead and compute this with a problem. Let's take a look at our first example of triple integration, and this time we're going to look where our region of integration is a box, and really I should say our volume of integration is a box. So in this case, our density function is given by f of x, y, z is equal to 2xy plus z, and the volume that we're integrating over, in this case, is a rectangular box. So my x coordinates are going from 0 to 2, my y coordinates are going from 0 to 1, and my z coordinates are going from -1 to 1. By convention, we always write them in order x, y, z. So rather than drawing a picture of this, let's go ahead and just compute the integration. So in this case, the function that we're integrating over is going to be the function 2xy plus z, and we're going to do a triple integral. And in this case, just like in our other case, we can apply Fubini's theorem for triple integrals. This isn't actually the word triple, but you can follow what I'm saying. So Fubini's theorem for triple integration tells us that the order of integration for rectangular regions doesn't matter. And really, I should say for rectangular regions, I really mean volumes, because a region typically is just down in the xy plane, whereas in this case, we have a whole volume, this rectangular volume. And because the order doesn't matter, I can just arbitrarily choose it whichever order I want. Let's say I'll start with my integration with respect to x first, then compute my integration with respect to y second, and then my integration with respect to z last. What does matter is that I make sure that my integration bounds always match the order of my differentials. So if I start with my bounds on x, it means I have to take my integral with respect to x first. So let's go ahead and start computing this integral. To integrate this function with respect to x, I treat both y and z as constants. And so to integrate my x term, I end up with the constant 2. I raise x to this second power, I square it by polynomial rules. Y is just treated as a coefficient. Z is also treated as a coefficient, and by integration, I need to integrate a constant term z becomes x times z. The reason why I know this is because if I were to take the partial derivative with respect to x, it should get me back what I want. And the derivative of this term is going to end up being just the z term. So in this case, I've taken my integral with respect to x. I need to evaluate it as x goes from 0 to 2. Don't forget about the remaining integrals that just sort of are going to hang out on the outside. I can evaluate this. I see that my 2 times 1/2 cancel with one another, so I'm just going to simplify the problem by canceling those two. And I see that when I plug in 2 for x, I get 4y plus 2z. When I plug in 0 for x, both of these terms become 0. So now I'm left with a double integral with respect to y and with respect to z. I'm going to continue the rest of this. The integration follows as you might expect. So my bounds on z, recall, we're going from -1 to 1. My bounds on y are going from 0 to 1. I was just lazy and not writing those bounds in for those parts, just because I wasn't really worried about what was going on for those sections. dy dz. So now I think of taking this next innermost integral. I'm going to integrate this function with respect to y. If I integrate this with respect to y, I see that I get 4 times 1/2 y squared plus 2zy. Integrating with respect to y treats z as a constant, so this is a constant term that becomes 2zy. I evaluate that from where y goes from 0 to 1, again leaving my final z integration on the outside. When I evaluate this, I see that I get 1/2 times 4 is 2. When I plug in 1 for this function, I end up with 2 times 1, which is just 1. When I plug in 1 for this function, I end up with 2 times z times 1, which is 2z. When I plug in 0 for y, I get nothing and nothing, so I don't have to worry about those terms, which means that now I'm just left with one final integration where my z value is going from -1 to 1 dz. This is an easy thing to integrate. I integrate this, the constant term ends up becoming a z, plus 2z, I'm going to square it, and I get 2 times 1/2 z squared. And I evaluate this from z equals -1 to 1. Plugging in 1 for z, I get 1 plus 2 times 1/2 times 1, which is just 1. So I get 1 plus 1, which is 2. And then I subtract out -1 for z. So I plug in -1, and then z squared becomes -1 squared, which is +1 times 1, which is 1. So -1 plus 1 is 0, and I end up with a final solution of 2. The steps that we took are exactly analogous to the steps that we took previously when we were doing double integration over rectangular regions. The one final thing that I want to point out, but I'm not going to actually compute, is the fact that if I decided to take these integrals in a different order, that's totally fine. Fubini's theorem tells us that instead of starting with our innermost integral as x values, I could shift these, and if I wanted to, I could start with whichever values I wanted. Let's say that I wanted to start with the y values first. I would have to make sure my bounds on y matched the y intervals. And then I could switch and have maybe z next. So my z's go from -1 to 1 dz, and my x's could be my final bounds of integration dx. I just need to make sure that in my order of integration, if my bounds are y bounds, that when I integrate, I have to integrate with respect to y. Fubini's theorem tells us that we can do this for rectangular regions. I'm not going to compute this. You'll find that if you did decide to compute this on your own, you would get the same solution that we saw before. We would get a value of 2 for this integral.